In this lecture, we will solve some numerical example. However, before going on to that, I will try to want to show you another form of magnetic field in the form of charge and the velocity. So we have seen that the magnetic field from Biot Savart's law is given as mu naught I over 4 pi dl cross r over r square. So where this r is from the source to the observation point. So now this I is given as Js dl dash or only Js, that is the current density into the surface area. So in a wire we are assuming that current density is perpendicular to the surface area, or J dot ds is equal to Js only. Okay, so I will put this here. So dB is equal to mu naught Js over 4 pi dl cross ar over r square. Now J, we have seen in our previous lecture, is simply written as if there are n charges per unit volume, then this is the value of, this is speed velocity of the charge carriers. So this is J. So I will write in place of J as mu naught n q, the speed, over 4 pi s dl dash cross ar over r square. Now this dl dash was in the direction of the current, and if we are assuming that there are positive charge carriers, then this v is also going to be in the same direction of the current or the current density. So I can transfer this sign, vector sign, to this. So I can write dB is equal to mu naught nq s dl dash v cross ar over r square, or dB is equal to, now this is the total charge in this volume as dl dash. So mu naught, the total charge, over 4 pi v cross ar over r square. So you see that this is another form of magnetic field. So if this is the total charge delta q, which is moving at its velocity v, and we want to find the field, magnetic field, at this point P, which is at distance r, then we just can directly find the field B, simply mu naught delta q over 4 pi r square v cross ar. So this equation is usually not found in any textbook. It is rarely found, and in some textbooks where it is given, then it is taken as the starting point, and from that all the equations are derived. And I found that it is giving more physical, intuitive explanation. That's why I wanted to show you this form of magnetic field, which is usually not found anywhere. And you will try to see the physical explanation to it, why there is a magnetic field when the charges are in motion. So this is how you can find when charges are in motion, the field, because the magnetic field, because of those moving charges. Now in the next slide we will solve a numerical example for finding the field of a finite length wire. So let us see what is the question. So we are given that there is a wire of length 2L. So this wire is having length 2L, and we need to find the magnetic field because of this current carrying wire. The current is in Z direction, and this is Z direction only. Okay, this is Z direction. So we need to find field at this point P, which is at a distance r from the center of this wire. So this is r. Okay, this is center, and the total length is 2L, so it will be L and L. Now we need to find the field due to this wire at this point P. So we will solve in two ways. First we will find the magnetic vector potential, and then from that we will find the field. And in another way we will directly use Biot Savart law for solving the field directly. So let us take this is small current element dl dash, which is at z dash from the center. So this will be r. So dl dash can be written as dz dash az, and r is simply r square, sorry, z dash square plus r square, this plus this from Pythagoras theorem. So now using a is equal to mu naught I over 4 pi dl dash over curve c dash over r, we can easily now find the vector potential. Now since we are given that wire is from minus L to L, then we will just remove this closed curve sign, assuming that it is a part of some circuit. Then we can find A is equal to mu naught I over 4 pi from minus L to L dl dash over R is equal to mu naught I upon 4 pi z dash square plus r square under root and dz dash az. So we can now easily solve this. This is a standard integral and found in various integral tables, and from solving you can find that it is equal to az mu naught I over 4 pi natural log L square plus R square plus L over L square plus R square minus L. You can solve it by just putting Z is equal to R tangent U. So by just replacing this in here, you can easily solve this here. Now we need to find the field. So field is equal to B is equal to del cross A. Now in cylindrical coordinates it will be equal to del cross az is equal to AR. In cylindrical coordinates you can easily find del cross like this: 1 by R dou by dou phi of AZ minus A phi dou by dou R of AZ. Now because we are finding field from the center only, that is which is at a point which is distance r from the center, so you see that field will be like this only. So it doesn't matter whether we are measuring here or here. So if it is at the same distance, then it is not going, the magnitude is not going to vary with the angle. So dou by dou phi of AZ is equal to 0. So this will be 0. So B is equal to minus A phi dou by dou R of AZ is equal to minus A phi dou by dou R mu naught I upon 4 pi natural log L square plus R square plus L square plus R square minus L. On solving we can find B is equal to A phi mu naught IL over 2 pi R L square plus R square. Now we can verify whether we have done it correctly or not by taking that we are very near to this wire, that is this R tends to 0. For this case, we will see that this wire is now infinitely long because we are very near. We are like an ant which is seeing this wire that it is very big now. So this equation should reduce to the field due to an infinitely long wire. So let us put r is equal to 0. So it will be a phi mu naught I over 2 pi r. So this proves that we have a valid result. Now let us find the same field by using Biot Savart law. So B is equal to integral of dB. Now here again dl dash is equal to dz dash az, and r is equal to rar minus z dash az. From the triangle, this is rar, this is z dash az. So you can find this r is equal to this. So dl dash cross r is simply az dz dash cross ar r minus az z dash is equal to a phi r dz dash, because this into this cross product will be 0, only this will survive and it will be equal to this. So b is equal to mu naught I over 4 pi dl dash cross r over r cube is equal to mu naught upon 4 pi I minus L to L r dz dash over z dash square plus r square power 3 by 2 in the direction a phi. On solving, it is simply a phi mu naught I L z dash square plus r square under root o into 2 pi r. So it will be same which we have calculated earlier. So in this way we can find field by using these two methods, and for a finite current both are easy, although in the first process we had little more calculations. Here again this integral can be solved by putting z is equal to r tangent u. Now in the next slide we will find the magnetic field on the axis of a circular current carrying loop. So let us do that. So this is a current carrying loop which is circular. This is current I. Let us say this is axis y, this is x axis, and this is z axis, and it is along the axis of this loop. So we need to find, let us say, field at this point at 0 0 z. Okay, now let us take a small element dl dash which is at phi. The radius is, let us say, b. So this will be r. It is straight actually, make it straight. So this is r, this is b ar, this is z az. So r vector is equal to z az minus b ar, and dl dash is equal to b d phi dash a phi. So from this r is equal to z square plus b square under root. So dl dash cross r will give us b d phi dash a phi cross z az minus b ar. So solving, we will find it equal to bz d phi dash ar plus b square d phi dash az. Now you see that in the ar direction the field will be cancelled by an equal and opposite contribution from the symmetrically placed current elements. So this will, let us say, create a field whose r component will be like this, and this will create a field whose r component will be like this. So both will cancel out, however the z component will not cancel out. So we will not calculate this because it will get cancelled out, so only we need to calculate this. So b is equal to mu naught upon 4 pi I, phi is varying from 0 to 2 pi, b d phi, b square d phi dash in the direction of az over z square plus b square power 1 cube, so 3 by 2. So it will be equal to az mu naught I b square over 2 z square plus b square power 3 by 2. Now if I multiply and divide with pi, I will find it as like this. So it is az mu naught I into area over 2 pi, this is r cube, this z square plus b square, its power 3 by 2, it is equal to r cube. So now this quantity IAZ is called as magnetic dipole moment. So B is simply equal to mu naught upon 2 pi magnetic dipole moment over r cube. So in this way we have found the magnetic field on the axis of a circular current carrying loop, and we have defined the magnetic dipole also, but we will find magnetic field as well as potential at any point due to this dipole at a very far point in the next lecture, and we will see in detail in the next lecture. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel and join our Telegram group, whose link is given in the description of this video. Thank you.